Go! I know the triangle is a little bit skewed because I had to stretch it out, but assume angle C is a right angle. You are given 3 measurements. Solve the triangle. Remember, solve means find everything that's missing as accurately as possible. And then also find the secant of A while you're at it. As simplified as possible. Which one of those is more accurate?
What's the degree of every angle, please? Okay.
Solve means you find everything that's missing. You are given that AB is 8, BC is 6, and angle C is 90.
AC.
You got to catch them all. Power of Christ compels you. See a little bit of monkey button pressing, just double checking stuff. Anyone need more? A little bit? Okay. That's cool. Got it. Cool. Jace?
Yeah. Does it make it true?
Okay.
180?
All right. So, step 1. I'm going to put my 90 here just so I know. If I got a right triangle and 2 sides, then the most accurate way to find the third side is what? Good old cult leader Pythagoras. We're going to say that AC is the square root of, because I'm finding a leg, hypotenuse squared minus leg squared, or 8 squared minus 6 squared, which is 64 minus 36, which is 28, which is 2 root of 7. Simplified. Okay, as accurate as we can. After that, if I'm going to find the angles, it depends which angle you found first, because if I find one, what do I do for the other? Just subtract from 90, add them up, subtract from 180, whatever your jam is. So I'm going to write both, but you don't have to have the calculation for both. From B, I'd be dealing with adjacent and hypotenuse. So I'd say measure of angle B is arc cosine of adjacent over hypotenuse. If you had said 3/4, also cool.
It's really messing with me because the triangle doesn't look like they should be.
I just stretched out a random triangle and threw numbers on there. What is that? Ballpark.
41.4096.
4096. So if I go 3 places, if you went more than 3, great. But if you just said 41, that's cool. Or if I had found angle A first, then I would have had an opposite and adjacent. I'd say measure of angle A is arc sine of 6/8 or 3/4. We'll take either one because they'll reduce down. And that would be the complement of, so 48, 59. Again, you only have to have the calculation for one or the other. I understand you just subtract from 90 to get the other one. Okay? And finally, secant. Secant of A is going to be your hypotenuse over your adjacent, which is 6/2√7. I know there's the domino effect there. If we goofed, you. Whoa. Y'all should have been louder. Y'all should have. Man, first hour would be screaming for blood right now. No. Okay, 4/7, we can't have that. Rationalize. Colors 4√7/7. So, you had to find 4 things, and we'll leave that for the whoopsie. Like, I did the calculation, I did the arc thing, I forgot which side was adjacent, which was opposite. So, like, I found this for A and found that for B, kind of thing. Or maybe over here you just used one of these values to then write a decimal. So it wasn't 2√7, it wasn't accurate. Because, do you see now why we wanted that side to be 2√7, not 5 point blah, 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 blah? Because you had to go find the secant, and I can't find a secant with a reasonable accurate value if I have a decimal over here. Okay?
So that number would go on forever.
Yeah, it's an irrational number. Irrational means it is a non-terminating, non-repeating decimal. It just goes off to infinity, making 0 sense. Wait until you get to discrete math in college. You're right, for now. Homework. The only question I received was someone double-checking their word problem. Well, 2. One was making sure they set it up right. The other was, I swear I set this up right, why didn't I get the same answer? And they just wrote as 8 instead of a 0 somewhere. Oops, it happens. Anything about it? Were you cool with the ratios on 4? When we say it is a trig ratio, a ratio is a comparison. So I literally say that if my ratio is 1 to root of 3, then I just say 2 is in this spot, square root of 3 is in that spot. You set them up. This is in the root of 3 spot, this is in the 2 spot. Cross, multiply, solve. That's it.
What?
It's a 30, 60, 90 triangle. 30, 60, 90 triangles will always have that ratio. So, if the hypotenuse is always supposed to be twice this side, if the long leg is always supposed to be root of 3 times that side, then I can say the root of 3 spot and the 2 spot compared to this expression and this expression, cross, multiply. And even though it had radicals to begin with, it comes out clean when you do that. Okay, so everything on this, everything that we did yesterday, it was all geometry. Today, we're going to do something that is supposed to be in middle school math and geography. Turns out it wasn't. We're also going to get the definition of the radian angle measure, which was supposed to be in geometry, which wasn't. So I don't think anyone except physics knows what we talk about today. So this should be new stuff. Does Gabe even have you actually work with radians at all, or does he?
It's more of like a unit, kind of like a radians per second.
That's the only, okay. So less with the unit circle, more just, here's my conversion factor done? Okay. Just checking. Boop. Then, Frank. Oh. Starting with a circle, we all know is 360 degrees. Do you know how to break that circle up into the various measures that are important? Okay. I want you to look at those numbers and tell me, what do you notice about the pattern between them? Like, what are they counting by? Or what could you count by? Okay. They're all in increments of 15 or 30 degrees. Specifically, what's 15 plus 30?
45.
I'm talking about 30, 45, 60. Where do we know those? The special right triangles. When I said you're going to make that unit circle this chapter, but it's not nearly as complicated as it looks because it's just the special right triangles on repeat. It's because these are the special right triangles on repeat. If I take 360 degrees and I chop it in half, 180. If I cut those in half, anyone here work at a pizza shop? Who can't cut a pizza straight to save their life? No? You always got that one person who's like, okay. When I cut a circle into quarters, you remember your quadrants. The reason that we have quadrants labeled 1, 2, 3, and 4, and the reason that these numbers go in this order around the circle is because a positive x to a negative x, a negative y to a positive y, on a normal coordinate grid, we call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Which is why my angles are measured counterclockwise for positive angles. Okay? It bothers some kids. There was a big old argument first hour about 0 should be at the top of the circle.
I just realized it's
Because we start off to the side here, it says it, the positive x-axis is considered to be standard position. I normally start with positive x's whenever I'm graphing things, whenever I'm talking about domain and range. We like to talk about domain before range. We like to talk about positive numbers before negative numbers. So all of these angles are going to be based on, I will start at positive x, and then I'll rotate counterclockwise for positive angles, or I'll rotate clockwise for negative angles. And we're going to start talking about angles that end in the same space are called coterminal. They're not the same thing, but they end in the same spot. Just like this, it's a finger, but it's also a thumb, right? Do you ever, I'll meet you over at Walmart and you and your friends like race over there to see who gets there first, right? Don't do that. Bad. But you might take different routes, but you both get there. Since your routes were not the same, it's not the same angle. This may be a positive 45, but this is a negative 315. Because you can rotate either direction. And to denote which direction we went, we're going to say positive or negative. Righty-tighty, lefty-loosey, right? So,
or you could just have all the same, be all positive or all.
Yes. In fact, that's where we end off, is talking about positive, negative coterminal angles, where we graph them by drawing spirals. Okay?
In graph them, there's like an equation.
We barely scratched the surface of it today. Wait till next week. If I were to count by, well, these are by quarters, so these are by 90 degrees. If I were to count by 45s, that's the same as just cutting each of those quadrants in half, right? Now, each of those chunks is 1/8 of the circle. It's also 1/4 of the semicircle, right? This is all important. If we know fractions, then radians aren't going to be a big deal. I could have also counted by 30s instead of 45s. If I went 30, and then 60, and then 90, then 120, 150, 180, and so on. Every one of these special angles is my 30 or 45 or 60 degree increments. Okay? These are numbers that you got to know. If I just draw a random angle, you should be able to tell me what quadrant it's in. You should be able to ballpark which of these it is. Now, obviously we can get 206.3 degrees. But most of what we're going to do in this chapter is working with these specifically because they're based off the special right triangles. Do you see the whole bunch of special triangles in there? Like, here's your 45, 45, 90 triangle. Here's your 30, 60, 90 triangle. Okay? That unit circle is just those triangles on repeat. Okay? So, we have standard position. We'll always start with positive x-axis and rotate counterclockwise. Or if I go negative angle, I'll go clockwise, the other direction. You have your initial and terminal side, blah, 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 old school geometry. New definition. Well, not new. It's this entire example is just a side quest so you can understand word problems. Because apparently this is something that you did not do. Maybe you saw it in middle school, but you definitely didn't do it in geography, is what I'm hearing. Geography. Can y'all read a map? Do you know how to find the latitude and longitude of a location? Did you know that latitude and longitude are not just a bunch of strings of decimals after thing, that they come off of the degree, minute, second system, and that's how we navigated the world prior to the Google location app. Degree, minute, seconds is how most maps are built. Anyone do a lot of hiking? No? Go out in the hills? Anything like that? Okay. So probably not fancy enough to have your minute maps from the Forest Service. No?
There's an app.
What? It's just. What about? I'm somewhere that doesn't have service.
You can download it.
Oh my god. Your generation is spoiled. Okay. In the ancient times.
No.
Like,
They didn't have a
back up 5,000 to 1,500 years. Like, oh, sorry, 500 to 1,500 years ago. Once they discovered Earth round. Okay? The idea was, what is round that I know about? Well, I know about circles. Circles are broken into 360 degrees.
When did
So,
they understand circles? What time period? Because then it like really buzzed one for a while.
it depends whether you're dealing with whitewash history or with actual history. The mathematical history says that the Indians and the Mayans had this thousands of years before the Greeks even looked at it. Okay? You're going to hear a lot about Greek mathematicians, but thousands of years before that, other cultures had this. It's just our history is very biased and incorrect. The idea was 360 degrees. A degree is literally just 360, or 1/360th of a revolution. Like, it doesn't have any special definition beyond that. They chose 360 because 360 is divisible by a bunch of things. I can divide it into halves, thirds, quarters, sixths. I can divide it into tenths. I can just twelfths. I can go all over the place, right? It's very divisible, which means I'm able to chunk up into fractions a circular space.
Nice.
Okay, nice fractions. So we had lines of, do you remember the difference between latitude and longitude? Which one's which? Okay, assuming that this is actually round. I'm not doing a very good job. Okay. So, which one's latitude, which one's longitude? Okay. I always remember it as, like, it don't look like it now, but used to live in the weight room doing lats, right? Lats are sides. Okay? Lateral movement. Any of you done different sports training where you're doing lateral movement to work on, especially if you bust up your ACL or your MCL? Okay, lateral is this way. Longitude is this way. Ironically, lines of longitude are shorter because the Earth is fatter in the middle. Well, it is. Like, take a basketball and spin it really fast. If you can get it on a slow-mo camera, you'll actually see it compress a little bit because centripetal force is going to force the outside further out. That happens to the Earth. The Earth is not a perfect ball. It's more like an egg. Okay? So, in the ancient times, they break this apart into degrees. They use latitude and longitude, and they say, I'm going to break up the circumference of the Earth into 360 sections. I'm going to call them degrees. But then, that's a huge honkin' space. The circumference of the Earth divided by 360 is still a really, really big number. So, they said, I'm going to take this 1 degree by 1 degree space, and I'm going to break that space up too. I'm going to break it up into, I'll call it minutes. Because something else that's circular that we all know very well is a clock. Okay, they're using things that people would understand as they're trying to navigate. I know that a clock has 60 minutes. So I'm going to take this section, and even though it's 1 degree by 1 degree, I'm going to say it's 60 minutes by 60 minutes. I'm going to break it up into 60 by 60 chunks. Okay? Well, 60 minutes by 60 minutes, that's 1/21,600th of the circumference of the Earth. That's still really big. A minute map is still going to be, I forget exactly what it is, like 30, 40 miles in each direction. I can still get way, way more detailed than that, so I'll take this section. Well, I'm going to keep going with that clock, and now we're going to say that 1 minute by 1 minute is now 60 seconds by 60 seconds. Now, if you go all the way down to a 1 second map, you're looking like at the core of Spearfish. Like just the downtown and residential areas. That would be like a second. 1 second by 1 second. The reason I bring that up and hiking and all that kind of stuff is you can go to the Forest Service and you can get what are called minute maps. You've seen at least topographical maps, right? Where they've got the terrain and the elevation shown, where you got all the squiggle lines, and the closer the lines are together indicates that it's steeper, right? Those topographical maps are usually done as 1 minute by 1 minute. And you can get them from the Forest Service if you want to go out hiking in the hills and you have a physical map that is extremely detailed. So, degrees, minutes, and seconds is how the ancient ones broke up the Earth. And just like feet and inches are shown with 1 tick mark and 2 tick marks, minutes and seconds are shown the same way. Okay? So I'm actually going to do B first. If I have 32 degrees, 5 minutes, and 28 seconds, and they want to turn that into a decimal, I have 32 whole degrees, I've got 5 minutes, which is part of a degree, and I've got 28 minutes, or seconds, which is part of a degree. How many minutes go into a degree? 60. Careful. How many seconds go into a degree? 3,600, right? It's 60 by 60. So if you want to write 3,600 or you want to write like 60 squared, whichever way helps you remember that better. But it's over 3,600 or 60 squared. If I want to turn this into a decimal, I just jam this in my calculator. I'll have 32 point blah, 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 blah degrees. So, pressing monkey buttons. Make sure you're in fraction mode. If you're using parentheses and division, be careful with the parentheses. It won't matter for this. Degrees and radians will not matter on anything we're doing unless we are pressing the sine, cosine, and tangent buttons. 099? Oh. Okay. Oops. Degrees. So, degree minute seconds over to just degrees, or using that same concept, work backwards. If I'm given the decimal and I want to go to degree minute seconds. You remember, when we were first doing our regression stuff, and it was like, when is the value of this stock going to be $30? And we had said, well, it's in the year 2014. And I said, but couldn't we keep going? We could also say, in what month? And then I could say, in what day, in what hour, in what minute, and so on. I'm using that same idea of breaking up the decimal. I have 56 whole degrees, and then I've got 0.735 of a degree. But if I go down to the next unit, the next one is minutes. How many minutes are in a degree? Just like if I had part of a day, I would take it times 24. That many times 24 hours. I'm going to do the same thing here. But we have to find that decimal first. So then I'm going to have 56 degrees. And if I take 0.735 times 60 minutes, I get 44.1 minutes. I don't want to have 0.1 minutes. I want to keep going. So then I'll say that's really plus 44 minutes plus 0.1 times how many seconds in that minute? 60 again. Just like after I found hours, I would then take the decimal to find minutes, and then I would take the decimal to find seconds. So I've got 56 whole degrees, 44 minutes, and 6 seconds. Okay? Y'all, metric is superior. Like, just raw decimal. Metric is superior. 0.1 by 60. Because I had that much of a minute left over, and I didn't want to call it 0.1 minutes. Metric is superior because it's base 10 system. Easy to work with, easy to convert around. The customary, or sometimes called imperial, system of measurement is messed up. Y'all been in physical science, switching back and forth between inches and yards and feet and miles and gallons and cups and quarts and ounces. It's all just random numbers that someone came up with. Okay? Way to go, England. But you need to know this because there will come a time.
Are these meters and stuff like by tens?
I said,
Quarts and all that crap is just.
the reason I need to know this is I might have something like city A is at 68.239 degrees latitude, and city B is at 16 degrees 7 minutes 12 seconds latitude, but they're on the same line of longitude. How far apart are they? You would need to have the circumference of the Earth and plug it into our arc length formula. But I'm not going to be able to do that at all if these are in different measurements, or if they gave them both to me in degree minute seconds. So this is why I asked if you had done it in geography before, because distance between locations on a map, you should have done something like this so you could learn to read maps that have the DMS system. And what I'm hearing is a big fat no. We colored things, right?
Use the scale.
Okay. Oh, at least we got that going for us. We did scales. So each of these, one's in decimal, go to DMS. One's in DMS, go to decimal. There you go. So just convert one over to the other. And then, if I remember right, where are you? Same. Where are you? 0.875 by 60. How much? So I turn that into 52 plus 0.5 by 60, getting a grand total of 213 degrees, 52 minutes, half of 60 is 30 seconds. If I have something that is in DMS and I want to switch over to straight decimal, 89 degrees plus 56 out of 60 degrees plus 7 out of 3,600 or 60 squared degrees, getting a boot. Frank. Get over there, Frank. Wake up, Frank. Any day now, Frank. Come on, Frank. Y'all notice how much slower it is with that streaming software running? And that's with the old laptops. The new laptops couldn't even run my streaming software and an open window at the same time. All right. Quit. Okay, first hour was being squirrely. I didn't show him this. Oh, you mother. I hate you. Frank. Hey, there we go. Win. All right. This was 214 point who what? 213.875. 213.875 degrees, right? Look above apps for angle.
Oh my gosh. I don't even know.
Switch over to DMS.
You didn't even show them?
No.
That's rude.
They were being squirrely. I had to hit one of them with the inflatable bat. Yeah. Okay. You can also use the degree, minute, and seconds are on the angle page. They're all right there. Okay. So I just wanted you to see that. So if you run across a word problem that involves location and the location is given to you by latitude and longitude with either form, you can do it. Okay? All right, that was the side quest. We were just talking about circle and breaking it up into our fractions and all that kind of business. Here you go. Ba-da-ba-da. He's been talking about it all year. We didn't know what it was. Let's talk about radians. Come here, Jace. Assume, it's not quite the same, but you get the idea. You ever wrapped a string around something circular? Like, did you do the calculate pi thing in middle school? Where everyone wraps a string around, you do your water bottle, you do yours, you do around the base of a flower pot or something. Everyone does that, and if you take circumference divided by diameter, everyone gets about 3.14. Okay? If you've ever done that curve around it, like arc length, what if I took the radius of that thing and said, I'm going to go that far around the circle, and then I just stopped. I can go that far around the circle. Stop. That's a radian. 1 radius of arc length is equivalent to 1 radian of rotation. And the nice part about that, see, they took this radius, and they're going to go that far, and that's going to be a radian. Okay? Nice part about it is that it doesn't matter how big the circle is. If the circle's this big, or the circle's this big. If the radius is this long, and I go that far, that is 1 radian, right here. If the radius is this long, and I go that far, it's still 1 radian. Doesn't matter how big the circle is. Where radians are nice is, normally we're talking about degrees as portion of 360. I would write that as a coordinate to x and a y. I'd have to have multiple measurements. A radian allows everything to be self-referential. Everything in it is dependent on that length of radius. And, fun part, that radius goes almost to 180 degrees. It goes there 3 whole times with a little bit left over. What do you think that little bit left over is? Uh-huh. And that's the big kahuna. That's how I go back and forth between degrees and radians. This right here is 180 degrees, but it's also pi radians. This is 180 degrees. It's also pi radians. It doesn't matter how big the circle is.
So that's why you get 2 pi.
And that's why a circle is 2 pi times radius. Radius is radians. You're going to start seeing a lot of those connections in this chapter. Okay, at the top, next to this, I want you to write, because this is a huge, huge deal, that 1 radian, which is rotation or angle measure, is equal to 1 radius. which is length. Who drives? Okay, most of us. When you're driving, your two most important gauges, well, three if you probably want to count gas. Speedometer. What units is speedometer in? Okay, unless you go up to Canada, it's miles per hour. What kind of measurement is that? Length or rotation? Miles per hour. Length. It's telling you, it's telling you how many of this length you will do in an hour. Right? Length. That is called linear speed. The one right next to it, the one that goes into the red every time you stomp on it to get around grandma, floor it up to 4,500. RPMs is what?
Rotations.
Okay. It's revolutions per minute, but, well, okay, we do rotations per minute. Stomp on it to get around grandma, and that flies up to 4,500. Think about that. The thing inside of your vehicle is spinning 4,500 times per minute, which is why it puts so much stress on the engine, and you shouldn't do that. It's basically like if we told you to sprint everywhere. Oh, bell rings, go to Spartan time. Just, you're always going to sprint everywhere. Okay?
Some things can get up to like 8,000.
Mm-hmm.
Like some trucks are just like 8,000.
If you've ever worked on farm machinery, where's our ranch kids? Okay. Farm machinery, God, I run a tractor. There's been times where you've really had to crank stuff to get through things. I'll get up to 11, 1,200. Like, you're burning some metal there. We need this. Tomorrow, this is going to be a big deal because you all remember back into physical science, where you would cross out your units. Okay? It's a big deal in trig and physics. A big deal. So we're going to be doing that again, and this is the portal. This is how you get from rotational over to length. Yes. That's how you go from one to the other. Has anyone ever gotten different size tires on their vehicle? Or you know someone who has? Of course, we're in South Dakota. How many of the Hicks out here went and put their big swampers on, right? Okay, my truck, when I first got it, it had the factory tires on it. I moved snow. I was sliding all over the place. So, after a couple of years, when their highway tires are nice and bald, I went and got new tires. Guess what? The radius increased a little bit. Had a little more aggressive tread on it. You know what else changes when you change the radius of the tire? Your speedometer. Because it's calibrated for a particular radius. So I had to change from this many miles per hour to deal with the rotation, because now one rotation of the tire goes further. It's going to say that I'm going 65, but really, because my tire is bigger, I might be going 67. I had to take that into account. Now, normally, if you go to a decent shop to have it done, if you're not doing it yourself, they will adjust your speedometer for you. Okay.
Great excuse.
They don't care. However, when I can rattle off the math behind the conversion factors to tell the cop, No, I was not going 32 and a 25. You're saying I went 32 because all of your tickets start at a minimum offense of 7 miles an hour over. That's why you're saying 7 miles an hour. I know for a fact that my speedometer said 31 and it's 1.5 miles per hour fast because I did the math. I teach pre-calc at the high school. You are not telling me the truth.
I actually knew that.
Mm-hmm.
7 or 5?
7 is the minimum ticketable offense in spearfish.
Yeah. Well, that was 5.
They'll lie. They'll say that you're at 7 even if you were at 5. They'll pull you over at 5. They'll pull you over at 3 if they don't like you. Yeah. Yeah, they'll pull you over just so they can check you. And they'll always give you a warning unless they can claim that it was 7 plus.
How do they claim that?
Lying. They're cops. Anyway, rotation. We said that one full rotation, 360 degrees, was, well, if this was pi, if 180 degrees was pi radians, then what is a full rotation? Right? That's where we get that circumference from. 2 pi radians. Now, I'm going to stop writing radians after this page. Remember when we said if you don't put that little degree symbol on there, we assume it's radians? So after this point, we're just going to see angle is 7 pi. I assume that's in radians. Okay? All right, what if I start chopping that up? Notice that pi was half of the circle. So when I say 1/4 of a rotation, how far of the way to pi am I going? 1/2. 1/4 of a rotation was 90 degrees. So 90 degrees is, we call it pi over 2 radians. We're not going to write it as a coefficient, like don't say 1/2 pi. Just write pi over 2, okay? If I say 1/6 of a rotation, again, use the idea that this is pi. 1/6 of a rotation, what's 1/6 of 360? 60. So 60 degrees is 1/3 of the way to pi. Pi over 3. So what would 45 degrees be? Pi over 4, because I'm 1/4 of the way to pi. What would 30 degrees be?
Pi over 6.
Because I'm 1/6 of the way to 180. Okay? The easiest way that I remember that is not to compare it to the full circle. If a full circle is 2 pi rotation, I do all of them by my semicircle instead. If I ask, where is hoop, 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 half, third, third. If I say I'm at 135 degrees, and this is 180, 0, since I know this is pi, I ask myself, instead of what portion of the circle, I ask, what fraction of the way am I through the calzone? The semicircle. I'm 3/4 of the way through my calzone. So it's 3 pi over 4. Which is what I'd like you to go back to that first page with and start labeling these. I forgot to do this first hour. Probably because we were so off base. So next to all of these, we're going to write our radians. We start with 0 radians. We know this is pi. What happens when I cut them in half?
You get a single pi radian.
Pi over 2. So count by that. 0 pi over 2, 1 pi over 2, 2 pi over 2. What? This is 3 pi over 2, 2 pi over 2, or 4 pi over 2, or 2 pi. If I count by 45-degree increments, you said 45 degrees was how much of the calzone? 1/4 of the way there. So 45 degrees is pi over 4. So just count by quarters. 45 is 1 pi over 4. 2 pi over 4, it's already there and reduced. 3 pi over 4. 4 pi over 4, and it's already there and reduced. What's next? At 225. 5 pi over 4. 6 pi over 4, it's already there and reduced. 7 pi over 4 at 315. And then 8 pi over 4 is already there and reduced. Okay, what if I were to count by 30-degree increments?
Pi over 6.
It's a sixth of the way, right? 180 divided by 30, 1/6 of the way. So this is 1 pi over 6. Careful, 2 pi over 6, pi over 3. 3 pi over 6, already there and reduced. 4 pi over 6. 5 pi over 6. 6 pi over 6. I want to see if you can finish those last 4. Keep counting by pi over 6. Reduce them when necessary. Seven pi over 6, 8 pi over 6, reduce it. 9 pi over 6, already there and reduced. 10 pi over 6, reduce it. 11 pi over 6. Now, this is just handy to have as we're learning radians, but didn't quite get there. There's also a conversion factor for it, and this is where Olivia's like, yeah, I know. The conversion factor, if I know 1 pi is 180 degrees, just like if I know 1 foot is 12 inches, didn't we always multiply by 1 foot over 12 inches or 12 inches over 1 foot? So, down at the bottom, if I want to go from degrees to radians, x degrees to theta radians, I'm going to multiply by pi over 180. If I want to go from theta radians over to degrees, just like the difference between 1 foot to 12 inches and 12 inches to 1 foot, I flop it. 180 over pi. I'll give you a prime example. Right above this, we have a couple. We said that 90 degrees was pi over 2. If I take 90 degrees times pi over 2, pi over 180, pi radians is to 180 degrees. Just like you're back in physical science, don't the degrees cancel out? You can cross out your units the same way that you can cross out factors. 90 is 1, 180 is 2, becomes pi over 2 radians. It's just I'm not going to write the radian part. Okay? So, whether I want to look at the fraction of a circle, or fraction of a calzone, that I'm looking at, or I want to just multiply by a thing, let's swap back and forth. First, before looking at the circle, do not look at the circle. Do not look at the circle. What quadrant is 120 degrees in? Second quadrant. Okay, we got to get used to it. This is 120 degrees. So think about how much of the way to pi are you?
3/4.
Not quite.
2/3.
Right?
2/3.
1/3, 2/3, 3/3, 60, 120, 180. I am 2 pi over 3, or 2/3 pi, away from 0 to 180. But I could also just take 120 degrees times pi over 180. Degrees cancels with degrees. Divide both by 10. 12 over 18 is 2 over 3. 2 pi over 3. Okay? So you could think of it in terms of fractions and the circle. You could just raw multiply it and be done. Your jam. Careful. Where is a negative 45 degrees? Which quadrant? Fourth. Right? I start at positive x. Negative means I turn this way, 45 degrees. So here's my starting initial position, standard position. I'm going to turn down this way, negative 45 degrees. And think about what fraction of the way are you to pi? How much of the calzone? A quarter, right? 45, 90, 135, 180. I'm 1/4 of the way there, so I could just say pi over 4, but I rotated this way. Negative pi over 4. I could also just multiply it. Take that times pi over 180. Degrees cancels. 45 over 180 reduces to 1 over 4. Either way works. 5 pi over 6. Think about the calzone. If I break this up into 6, and I go 1, 2, 3, 4, 5. 5/6 of the way there. How far? 150 degrees. Because 1/6 of 180 degrees is 30 degrees. So pi over 6 is 30 degrees. So just take pi over 6 times 5, 150 degrees. Or 180 degrees over pi, pi's cancel. 6 with 180, 5 times 30 is 150 degrees. Fractions or conversion factor. What quadrant is negative 3 pi over 2 in?
Negatives, so that is the second or third. Or What, it's right on the line?
It's not in a quadrant, it is the quadrantal angle. Because remember, pi over 2 is 90.
Yeah.
And it's negative, so I'm going to go 1, 2, 3 pi over 2's.
So it's like
No.
negative 90.
No. How far did I travel?
Oh, 270.
270. That's a negative 270 degrees. Okay? It's like, how far did you ride your bike? I went 8 blocks. Like, your house is just on the other street. I took the long way. You still went 8 blocks, so you better say it, right? If you went 270 degrees, you better say 270 degrees. And if you're not sure, you can always take that times 180 over pi. Pi's cancel. Half of 180 is 90. Negative 3 by 90 is negative 270. So it's your choice. I'm just trying to show you different ways to do it and different ways to think of it. Some kids think of this more algorithmically. Some kids think of it in terms of proportions. And I want to give it to you both ways because I know we have both types of thinkers in here. And if neither of those is making sense, you got to tell me because then I can give you a different way. I'm not going to lie. Years ago when I started saying how much of the calzone instead of how much of the circle, all of a sudden kids started getting it. Because it was the semicircle that mattered. I didn't think of that until I was working one-on-one with a kid, and they said, "Isn't that more like a calzone?"
So I did this one right.
Nailed it. Okay, teachers get better the more you work with us. The more you say, "Nah, that don't make sense. Try again." I would encourage you with these, instead of just doing raw multiplication conversion, try to think of what quadrant it's in before you do the thing. It's going to help with solidifying this unit circle as we're building it over the next few sections. All right. Contestant 1, what quadrant am I in? Third. 210 is past 180. So 210 degrees is how much of the way to the next pi? A sixth of the way there, right? Or 30 degrees of the way there. So if that's 1/6 of the way to the next pi, and this much is 6/6 of the way there, I am 7/6 of the way through the circle. -60, what quadrant am I in? 4. Negative because I rotate this way. And it's 1/3 of the way to pi. So negative pi over 3. 4 pi over 3. If I say I'm going to cut this into thirds and cut this into thirds, right? The top half is in thirds, the bottom half is in thirds. If I just count by those, here's 1/3, 2/3, 3/3, 4/3. 4/3 of the way through that circle. My angle is going to be 60, 120, 180, 240. Negative pi over 6. Is at negative 30. And someone this morning nailed it right on the head. A quick cheater for these is that n out of 2 pi's is 90 degrees, 90 degree increments. N pi out of 4 is what? What increments are pi over 4s? 45 degree increments. N pi out of 3 is what increments? 60s. N pi out of 6 is what degree increments? 30s. If you just count by 30s, 45s, 60s, or 90s, every time you see those denominators, you're good. It's just cutting up that circle like you're cutting up a pizza. Okay, coterminal angles. See, there's more than one way to get to Walmart. There's more than one way to spin and end up right back where I started. Right? If I am aimed this way, I could, if I want to aim at Emrys, I could turn like this, or I could turn like this. In either case, I'm still pointed the same direction.
Or you can spin 3 times.
I'll just get it out of our system. First hour, without any command, in synchronicity, I had 15 kids all stand up and start spinning next to their chairs. Because I told them, apparently y'all just don't stim like, some of us do. You can spin as much as you want in one direction, just do 2 laps in the other direction, you're fine.
For real?
Yes.
It works. I tried.
Because as you are spinning, the reason you get dizzy is because the fluid in your inner ear starts tilting up like this.
How do some
And it changes the pressure inside your ear. So if I whip my head around the other way, it balances it out. You can spin as much as you want in one direction and start getting dizzy, and then just go the other way. Then you're fine.
Yeah, how do some people not get affected
I
by
know they
this?
like stare at the ceiling and focus on one spot.
Yep. Because then it's everything around it is moving instead of the spot that you're looking at moving. Additionally, you're supposed to whip your head around
Yeah, maybe-
each time.
Oh, yeah, Indians is like spotting your
hmm
So that's how they don't like them to
That's also how you wreck your family at the family reunion, where you got to spin on the bat and then take off running. Everyone else falls over like they're hammered. You just go 2 laps in the other direction when you're done and go. It works. Okay? Coterminal angles are things that end in the same spot. I could have a positive angle that go this way. Where about do you think that is? It looks about halfway through the intersection, or through the quadrant.
240. Or
225.
Yeah.
45-degree increments, right? This is, it looks like anyway, 225 degrees, or 45 degrees are quarter increments.
3 over 2 pi. No.
Here's 1 quarter, 2 quarters, 3 quarters, 5 pi over 4. Now there was a different way to get there. I didn't have to go that way. I could have instead gone this way. Altogether, there's 8 slices on the pizza. 5 of them are right here. So how many are left? 3/4 of pi. And because I went the other direction, I call it a negative 3 pi over 4. Or a negative 135 degrees. They're coterminal angles because they end in the same spot. Where it gets dicey is when I've already got my positive angle and they say, go make another positive angle. I can't say 225 again because I already said it. So if I want a positive angle, I'm going to go to 225 and say, well, someone's in my spot. Go all the way around the block and try it again. Add 360. Or, if I was dealing with the negative angle. Well, if I wanted another negative angle, I can't go to negative 3 pi over 4. Someone's in my spot. So I'd go another negative 2 pi, another negative 8 pi over 4. Now I'm at negative 11 pi over 4. Or a negative 495.
So 10 pi over 4.
No.
The other one?
You would add 2 pi, which is 8 pi over 4.
Oh, yeah.
Okay? And can you go around a circle just once? Can you go around a circle just twice? You can go as many times as you want. What angle do we think this looks like? About 60, which is?
Pi over 3.
Pi over 3. Okay, it took us a while, but we got there. So if I want to get to pi over 3, or that terminal side again, I go to pi over 3, I'm like, oops, someone's in my spot. So I'll keep going around the block and I'll try it again. I have added another 2 pi, 6 pi over 3. I'm now at 7 pi over 3. Or I could keep going. 13 pi over 3. Or I could keep going. 19 pi over 3. And keep going and going and going and going and going. And you could be that one kid on the test who decided that their coterminal angle for this was going to be I'm just going to keep going. He tried to count out 100 rings.
What? And he drew it?
Yeah. Show off. I told him he could do it. He was pedantic. He asked if that's possible. I said, you absolutely can. But if you say that you added 200 pi to it, I'm counting your rings. No. You can go as many times as you want, which is what brings us to the bottom of the page. I can name all angles coterminal with something because I'm going to keep adding or subtracting either 360 or 2 pi. Which means my angle, they call it alpha, right? If it's my first angle, and then my second angle is beta, and you go Greek letters. I'm just going to keep adding iterations of 360. But I can't say plus 1.5 times 360, because that would be 1.5. I'm not coterminal anymore, right? I'm not ending at the same spot. So I need to make sure that this is what kind of number? One of those things from all the way back, lesson 1, day 1, integers, because I can do positive or negative, where n is a integer. The only difference for radians is instead of adding 360, what will I add? Full revolution. 2 pi. I'll say alpha plus 2 pi n, or 2n pi, depends who you're talking to, where n is an element of the integers. So if I wanted to know every single angle out there that is coterminal with 38 degrees, I'd say, okay, 38 degrees plus 360n, where n is an integer. Congratulations, I have just named every single coterminal angle out to infinity with 38. Okay? That's a good place to stop. We'll start drawing them tomorrow.
No, that's Arkansas.
The other one.
Hasn't been.